Alright, what's going on, people? What's going on? So word search, this is the problem of the day, given a 2D board, word finding existing word. So okay, A, B, C. So at the beginning, when I first tried this problem, I thought, okay, it's DFS. And it is DFS with backtracking. So its depth first search algorithm will work with backtracking. A little bit tricky to figure out the code, so I had to optimize. So getting the length of the board, iterating through all the rows, iterating through all the columns. If we find one that's equal to the first word, use visited set and a visited set and a visited array. The reason for having a visited array is because we're gonna backtrack and we're gonna pop from like a stack, because visited will be like a stack, and we want to pop from the last thing we added as we go back, and we want to remove that from our set. And the reason for the set is because it's quicker. We have O of our constant time lookup for any time we want to find where anything's at, you know? Yeah, so the constant time lookup is why we want to use this. So basically, this is a straightforward kind of concept. So if it returns true for our DFS search, then, well, we're going to return true. If it returns false, we're going to reset our visited and we're going to clear our set for our next iteration. And we just keep doing this. And if nothing works, we return false. Okay, so that part makes sense. Now let's see if DFS makes sense. So the DFS is, we take an I, a J, and a K. So if K is ever equal to the length of the word, we return true. So that means we reach the end of the thing. And so K is always the value, the next value we're looking for. So if the next value we're looking for is like equal to the length, that means we just, all values we're able to match. So here we search through, we do a depth first search, so we search left, right, up, down kind of thing. And we do it by iterating through this set, getting our new row and our new column. If these new row and new column are within our bounds, cool, we're good to go. And then we want to check if the board is equal to the word at K with these new row, new column, and the new row, new column are not in our set. So that's why we use a set. Then we're good to go. We're going to add this to our visited, append it, add it to our set, and then we're going to continue checking DFS. So we're going to increment K and go to the next one. If the DFS ever returns true, then we return true. If it returns false, then we'll go to this code, and this code is s.remove visited.pop, and so this has to do with the reason why we kept the visited stack, because we need to pop from the end of the stack when we backtrack, and then remove everything from, and remove that element from the set as well. One issue here is that so because this is DFS with backtrack, the time complexity is going to be, I guess, exponential, and I guess because we're backtracking on the word, so I mean, we obviously have an O in cube time complexity going on because we have this for loop, and then in here we have another for loop, and we're building a stack, and our stack could be about the length of the word. So we already kind of got O in, or OR times, oh, this is hard to talk about. So we have like iterating through the rows, whatever that is, times iterating through the columns, whatever that is. This is calculating my time complexity, multiplied by doing this DFS search. And in the DFS search, we're going to iterate through, well, this is a constant time complexity, we're just iterating through there. But we're going to keep creating a stack. So first off, that could be pretty big, the stack that we build. That will scale with the input for sure. It will especially scale with the word though. So we're building it, but then we're also backtracking. So that's going to make it, I think, exponential in terms of the word itself. So I believe the time complexity is already down. Time complexity is O of R times C times 4 to the power of the length of the word in S, if we say S equals, or S equals length, or word dot length. Now, so this is an okay solution, right? And why is this 4 exponential? Because we're going in 4 ways. Here. Can't get rid of this. Okay, so I'm going to analyze why is this exponential time complexity for this. Well, it has to do with the fact that it's backtracking in this sense. So let's say we search a word, right? And let's say we're at B. Let's say the next word is A. And A could be to the right, to the left, it could be below, it could be here. So it's kind of like the worst case. Like there's 4 options. And then look how big this tree is going to get. This is basically 4 to the 0. This is 4 to the 1. This is going to be 4 squared. This will be 4 cubed. And we're going to go, the size of this tree is the length of the word. So we could just call that S. So that means this could go all the way up to 4S. That's the amount of operations we could end up doing. Because at every letter, we have 4 places, 4 different paths we can start. And if we start 4 different paths for every letter, and we go to the end of the word, then we're generating this many paths, 4 to the S. So as long as a word is not too long, the time complexity should be okay. But if the word is really long, like this exponential complexity is not good. DFS backtracking is not the best algorithm. It's not optimized, but sometimes it's what is necessary to solve a problem. And it just happens to be one of those problems. But okay, so cool. So thank you for talking. Hopefully the discussion of DFS backtrack is helpful, and going over this code is helpful for solving this problem.